Before we had connected car data, most organizations have been or are still using traditional forms of infrastructure like roadside sensors, aftermarket GPS devices, traffic counters, and human capital to determine insights around how we get around this country. It's kind of like when we switched from the use of landline phones to a cell phone and explaining the why. Why do I need a mobile phone to get around? That's kind of where we are with connected car data, because what has been working has worked, but connected car data works so much better in a very different way. Wejo realized this opportunity with the increasing connected car market early on in 2014, and knowing that vehicles we drive know more than most agencies do. And we are now the world's largest connected car data company because of that. So how do we get our data? We partner with the world's leading automotive manufacturers, OEMs, and partners like Purdue University, who you'll hear from Darcy shortly, to really unlock the value of connected cars. We know, again, that our cars know more. And that really helps us understand the way that we work, live, travel, get from point A to point B. So the numbers, I'm going to give you a little context on Wejo, and then Matt, our data expert, will dive into some more detail, and then we'll hear this exciting case study from Darcy and Purdue University. So some numbers around the data set that we currently house at Wejo. We have access to over 18 million vehicles, and millions of those vehicles are live at any given time. Those vehicles stream data to us 24/7, 365 days a year. It doesn't stop. This data is not simply geolocation data, but it encompasses situational and contextual data. So things like driving events, driving behavior, harsh acceleration, harsh braking, vehicle movements, traffic volumes. And my colleague Matt, based in the UK, will share a little bit more about that shortly. We're receiving these vehicle attributes every 3 seconds. That gives our partners like Purdue University 650,000 data points per second at our peak. That data represents approximately 1 in 28 vehicles in the US, which gives us access to over 95% of roads all over the US, which, believe it or not, gives us more heightened information and greater volume than some of your traditional mapping applications. So this next piece is, why do we harness all of this connected car data, and why do we partner with global OEMs? To really sum that up, I think what Wejo is about, what we're trying to achieve is kind of how we see the public and private sectors and how we can support. So safety, it's a big one. 1.3 million deaths are caused by crashes globally. I think, a lot of you are probably familiar with Vision Zero. And through understanding behaviors and driving patterns of millions of vehicles, we can really start to inform these safety models and make a real contribution to less fatalities, heightened safety improvements, better driving experience, even on US roads around, the country, but also the world. Something I didn't mention early on is we are a multi-OEM platform right now. We are currently only in North America, but in 2021, we will be expanding to OEMs that cover other parts of the world. So we're growing along with the connected car market, and it's incredibly exciting. The other piece of this is economic value. $88 billion are wasted annually due to traffic congestion. Most of you, we tend to think of congestion being on main freeways, major highways, but a lot of that buildup is also in arterial and deep urban areas. And that's what our data set is able to show. And it's typically not some data analysis that you are able to achieve from some other modes of receiving mobility data without connected car data. So our ecosystem, what does our connected car data flow look like? How do you get your hands on it? Those types of questions. We do not employ any aftermarket devices in the vehicle. So instead, the vehicle itself is the transmittal method. We use LTE and we send our data via a 4G cellular network that will get upgraded to 5G next year. But this means that the feed of data that we receive is consistent and can't be manipulated, that we know that some telematics or cellular data collection, it happens. The data then makes its way through our proprietary platform. It's fully anonymized, and we conduct quality checks on each and every data point that pass through. So that data is then made available through a variety of ingestion methods and format, which Matt will speak a little bit more to. But it ranges all the way from raw data, which is, Purdue has the capacity and ability to analyze and look at the full spectrum of our data. We get all the way down to simple, like super simple traffic intelligence models that at the click of a button, you can see an intersection, you can see a moment in time, you can really understand, and a downloadable, digestible, somebody like myself in marketing, who's not, a data analyst, can really get it and know what's happening at that moment in that time. So before we hear from Purdue University about a more specific use case and case study within our data, my colleague Matt in the UK, our resident data expert, is just going to share a little bit more specifically about our data and how it works and what it looks like. Thanks, Matt.
Thanks, Blair, and warm welcome to everybody. To give myself my official title as opposed to data guru, data expert, I am the solutions engineer with Wejo. I've been with the business around 4 years. And I think what I wanted to kind of start to give everyone an overview around is the kind of Wejo data in a little bit more detail. So kind of covering off some of those unique attributes that we house and really how it can be used in a very kind of supplementary or complementary way to other data sources. So really kind of Wejo data kind of comes in, I suppose, 3 varieties. So the first of which Blair has touched on a little bit is around our drive and events data set. So that kind of provides event-based data such as harsh braking, wiper events, autonomous emergency braking, and things like seat occupancy at that event trigger level. Now, as each of these events also provides us with the geolocation data alongside it, it can be used for kind of analyzing things like concentrations of harsh braking events, which Purdue have done a lot of good work around, things like key intersections to inform signal timing changes. Secondly, we have our vehicle movement data set. Now that really does make up the heart of that kind of 400 billion waypoint figure that was mentioned previously. Now that provides data at that 3-second pulse from kind of over 10 million vehicles across the US. Now, as that data set actually has the ability to be streamed in kind of near real time as well, so near real time being sub 60 seconds, it's got actually the capability of being built into traffic optimization dashboards or TMC feeds as a good example. And then I suppose the final kind of data set is one around our traffic intelligence product, which is an aggregated data product. Now, really, that was designed to kind of solve the issue of big data, really by providing key metrics such as vehicle counts, average speeds, and stationary time in a very easily digestible CSV format. So kind of just before I kind of take you through the actual data in action, I wanted to kind of just illustrate for you probably the difference in connected vehicle data compared to maybe some of the other data sources that are available today that a lot of people, I'm sure, on this presentation will be aware of. So the 3 additional data sources that we've kind of looked at here are mobile-based telematics devices and kind of roadside sensors. So if we just quickly look at each of those in turn. So the green circle represents telematics devices and also mobile data. Now, telematics devices are available in abundance, but as I'm sure everybody is aware, they're extremely expensive to manufacture and maintain. And in some instances, like a UBI tracking device, they can be easily manipulated or removed, not entirely. Now, mobile-based collection, that's been around for a long time now. And whilst it gives volume, as we can see above in that illustration, it's got a very wide range in terms of accuracy against the actual road network. Now, in addition to this, often, inbuilt in a lot of the SDKs, the accelerometer readings in the cell phone will trigger and assume that that person is driving when in fact, they might be on a bicycle or even public transport. And then finally, kind of the blue circle, we have kind of roadside sensors. Now, these are typically used on major freeways and highways, but only really capture point in time or point in road data. So, also they don't have the representation on many surrounding tributary roads. Again, are very costly to implement. Now, by contrast, connected vehicle data is accurate down to a 3 square meter radius. And it's a true feed from the vehicle itself, and it comes from no aftermarket retrofitted devices, as Blair mentioned. And I suppose as a final point, we are seeing increasingly more and more companies using connected vehicle data to enhance their overall proposition and actually being able to contextualize and fill black spots in areas that they just couldn't get data in before. So really kind of wanted to share with you some visuals. I'm a very visual person, as I'm sure a lot of people are on this presentation, that really kind of brings connected vehicle data to life, and also to talk about some kind of practical applications in a kind of real world scenario. So this first visual really utilizes the event data set, and what we're seeing here is actually plotting of all of the harsh braking and rapid acceleration events in 1 minute segments. Now, the thresholds that are actually set in the vehicle is for both harsh braking and rapid acceleration is either plus or minus 2.67 meters per second squared for any of the techie guys that are on the call. So it's not just kind of a trigger of light hitting of the gas or the brake. Now, what we typically find with this data set is that it correlates very well to kind of known incident hotspots. But I think what's unique about this data set is that it actually develops insight into where the hotspot areas are and are likely to be, as opposed to when an incident actually happens. And then this second visualization actually utilizes the vehicle movement data set, and it really does illustrate that kind of 3-second capture rate and breadcrumb data that I mentioned previously. Now, as we can see, it's not only the waypoints themselves that are being captured through this data, but also the actual start and end point of the journey down to a 3 meter radius. Now, I'm sure a lot of people on today's webinar will quickly see the application around things like origin to destination analysis. But over and above those trends over time, really what the vehicle movement data has the ability to do is to provide context in many rural areas and tributary roads that it's just not feasible, but whether it be for cost purposes or just logistically to get that data. And I suppose just kind of coming to the end of some of the visuals here, we wanted to just highlight some of the kind of trends that we are kind of typically seeing more and more traction as we move through the market. So what we're kind of seeing here is a usage of connected vehicle data and being able to influence things like signal timing, which is very poignant for today's conversation, and actually make better decisions around intersection performance across the US. So, I heard a stat the other day, which was it's estimated that about 60% of traffic lights are not connected or kind of agile in any way throughout the US. And really our ability to verify changes to congestion in near real time, or even with a 24-hour delay, is really becoming a game changer in the market. So I think what you're kind of seeing from this video is our ability to actually infer things like queue lengths. So kind of when we start to look back on this queue here, we can see Wejo vehicles that are sat stationary still producing their lap long speed. They're heading every 3 seconds. So actually for influencing traffic signal timing, it's a very applicable data set. And then the second use case here is more around one that's kind of very close to very smart cities and municipalities alike, really around parking. So there was a stat that we saw earlier around, 107 hours per year that a New Yorker spends looking for a parking space each year. Now, because of the fact that we get ignition on and off events, or park in and out, as a lot of our customers term it, we're able to actually influence prediction models around parking demand. And it also has an application around things like large scale events or, major event planning. So every month we capture well over 2 billion parking events across the US. And really what this visual illustrates that it's not just the actual parking event itself, but it's the route and the time it takes for each driver to actually find that parking space. So I suppose as a final kind of slide from me, before I hand over to Darcy, I wanted to just kind of summarize some of the kind of applicable use cases and applications of connected vehicle data as it relates to those two data sets. So I suppose the few that I wanted to just pull out of this slide here were some of the ones that we've touched on already around things like driver behavior analysis on major roadways and arterials. That's a very common use case of things like the harsh braking and rapid acceleration attributes. But then in addition to that, the driving event data actually, the fact that it employs a persistent device ID over time, i.e. the device ID does not recycle, it means that actually our customers are able to use that data for plotting journey trends over time and then actually understanding things like dwell times at particular points of interest. So with that, that's enough from me, more than enough from me. It gives me great pleasure to kind of hand over to Darcy, who will kind of walk you through Purdue University's approach to optimizing traffic signal performance. Darcy, over to you.
Super. As soon as you, okay, I'll share. Okay, so thank you, Matt. I'm going to go full screen now. The context that Luke, Blair, and Matt laid out, I think, sets the stage well for my talk. I'm going to give you a briefing on work that the Purdue team has done analyzing some of the connected vehicle data from Wejo, and I think it's a really cool story. And the subtitle, or I guess before I jump into the talk, I just reiterate Blair and Matt's and Luke's comment to make sure you put questions in the chat box, because this is a team effort. It's kind of fun to get some questions as we go along. What I have subtitled my talk is that our vehicles know more about our traffic signal systems than we do. And I'll give you a little bit more detail on that, but I want to kind of first just put a couple definitions out there. And I'm really orienting this talk towards the traffic engineering community. So with regard to the definitions, I'm going to talk about a traffic signal system, and it's real simple: two or more traffic signals that we expect to work together in a coordinated manner. And Matt, you had a very good comment there about that 60% number you referred to in the United States. I absolutely believe that number. And I think the connected vehicle data is a game changer that can help us as traffic engineers do a better job, whether it be a corridor like this that is around a university campus, or a more dense corridor that's downtown Indianapolis adjacent to an interstate. So the numbers, I hesitate to guess. Matt and Blair made good commentary in terms of the number of records coming in. That number is going to continue to explode in the connected vehicle space. And from my perspective as a traffic engineer, and I think as I look through the attendance on this, how do we leverage that data to do a better job operating over 400,000 traffic signals in the United States? And quite simply, as Blair indicated earlier on sensors, that our past practice is to be cutting sensors in the pavement, having advanced telemetry in the traffic signal cabinet, and then trying to operate that. We're still going to do that, but if we can use the vehicles out there on the road to understand how our traffic signal system is operating, we are not dependent on having the capital cost invested in high fidelity controllers or extensive detectorization. So that's what excites me the most about connected vehicles. So I'm going to share with you some of the data that we have looked at over the last year with some of our partner states. We have a cool, fun study underway with several states showing up there, about 167 billion records just in the month of August. Today, I'm going to focus on the Indiana data. And I'm just going to show you a couple things. I start out with the hard braking because I think it's kind of fun from the safety perspective and illustrative of something that we can do almost immediately right now. So I'm just going to show the state of Indiana. State Route 37 is a corridor just south of Indianapolis. And we have 6.4 million hard braking events a month in Indiana. Matt talked about the G-force associated with what triggers that. And I'm just going to step through State Route 37 hour by hour. And as you see this plot growing hour by hour over 1 month of data, you will see certain hotspots start popping up. And then when we get to the end of the 24 hours now, I'll show you, this is where the locations, and if we look right here at this red circle, I mean, you can see, okay, this particular unsignalized intersection box pops up. Here, this location is a signalized intersection, and then here's that congested area there. When we have the ability to extract out, these are where those hard braking events are. That's critical because, and I'll have Wejo put a link in the chat window on this. It's an upcoming TRB presentation, but those hard braking events we can do with 1 month of hard braking data, what we could used to have to wait for 5 years of crash report data to come in. That's an absolute game changer. Instead of waiting 5 years for crash reports to come in, to be able to in a month kind of tease out with high statistical correlation between hard braking events and crashes where we might look. So upcoming TRB presentation, Wejo, one of my colleagues, will put a link to that in the chat window. And again, make sure you put questions in the chat box or the question box so we have some interaction at the end of the telecon. Now I want to shift, the title that Blair introduced had kind of a safety component to it and an efficiency component. So I showed you the hard braking and kind of showed you, okay, this is the sorts of things you can do with hard braking. Now let's look at vehicle trajectories. And I'm going to show you that same State Route 37 corridor. This yellow line is the posted speed limit and the ideal travel along that corridor. And I'm going to step through hour by hour, and that up at the top here, this little line will kind of move as I move through, and I bring in additional data records throughout the day. And if you look down here, this number here, the N equals 40, N equals 50, if you see how that bar is moving across up there, we keep adding in those trajectories, and I keep moving up to noon now. Just between midnight and noon, we got 1,200 vehicle trajectories. Stepping forward, kind of doing that Memorex fast forward, we can see that that's about 2,700 trajectories over that 24-hour day along that, pick your distance, that's probably a 6-mile corridor. So to be able to go out and harness that, and I'm just going to look at that intersection 4, that's shown here on the map. And I got this kind of red dashed line around that. And we're going to do a deep dive into those trajectories. And again, coming back to what can our vehicles tell us about the operation of our traffic signal at that location. And then I'll expand out that analysis at that intersection and show you how we can look at the operation for arrivals on green along the corridor. So Matt showed earlier some animation of the trajectories, and I'm just kind of show a close up here. These this red region are approximately 200,000 GPS points that have gone in the northbound direction through State Route 37 at South Point. So 200,000 individual vehicle positions. I'm going to now show you the analysis of. So before I do 200,000, I like to start with one vehicle, and I'm going to kind of step through this black line is the free flow travel direction, and then this blue line shows the direction of travel. And I'm going to show you some trajectories of vehicles moving in the southbound direction. Sometimes they stop. Sometimes they stop multiple times. But what we really want to look at is when we can start folding multiple vehicle trajectories. Here I'm showing you 270 trajectories that are moving through on green. These 141, they had to stop once. We can then come up with just a real simple representation or performance measure of what % of the vehicles arrived on green and proceeded through unimpeded. And this is between the 2:30 and 7 p.m. time of day. So to be able to, without going out there and doing any manual observation, without putting in extensive detectorization, without putting in an advanced traffic management performance measure system, we can use that data anywhere in the country to analyze and assess what proportion of vehicles were arriving on green. And then more importantly, and I think this is the graphic that I love to be able to kind of look at that big picture of how is our corridor doing, is I can look at all 8 intersections. So an intersection northbound 1, 2, 3, 4, 5, 6, 7, 8. And then the same thing in the southbound direction, 1, 2, 3, 4, 5, 6, 7, 8. And then I can look over, and this is for weekdays, from midnight, 5 a.m., 8 a.m., all the way up to 11 p.m. And I can see what percentage of vehicles are arriving on green. And I color code that real simply. If I have 100% arriving on green, I get these nice green boxes. If most of the vehicles are arriving on red, they get colored these kind of deep orange and deep red. So you can kind of qualitatively see how is the quality of progression along that corridor operating and what time of day. And so if you look at this one, you can see this is where if I was in a class, I would interactively and call on somebody. But you can see intersection 4 and 5, maybe our progression there at that 4 o'clock, 5 o'clock hour may have some opportunities to improve. And then similarly, you can look up here around the noon hour at intersection 1. So I hope you saw that. Now I'll just show you kind of in detail Fairview, another intersection, nice green color there. And if we look there, and I'll go to the next page, 95% of those vehicles are proceeding through there on green. So I'll just back up, and if you kind of see that relationship, here's the box, and what you mentally want to kind of scratch your head and say, I see that 95% of the vehicles are arriving there on green. The other thing that people like to get information about is what we call split failures, and they really want to know, do I have sufficient green so that when I stop at a traffic signal, I can move through? So I'm going to now show you the southbound direction at Southport Road. Another case where we got about 200,000 GPS samples, and we can put together these plots. And these plots are really quite simple. We talked about the green trajectories. Those are the vehicles that are moved through unimpeded. Most people pull up to a traffic signal. They're not, although they like to go through on green without stopping. If they pull up and they wait, they stop once and then they get to go through, that's reasonable. When they stop, have to pull up, stop again, 2 stops, that's indicative of a split failure. That says to us in the traffic engineering community, here's an intersection that has some green time that probably could need to be adjusted. And this loops back to Blair and Matt's introduction. How can we use connected vehicle data to identify opportunities to improve traffic signal performance? I talked about arrivals on green before. This is an example where we say, maybe we need to adjust that allocation of green to improve it. So what I'm showing you now here, and I can show you this I think kind of, we call them a bingo card, but the intersections 1 through 8 for both directions over 24 hours. And you can see at certain times of the day, pick your number there by that color coding, maybe 25% of the time we have vehicles that are experiencing a split failure. And the thing that's kind of interesting on this, and we can see it's really kind of concentrating in that probably 4 p.m. to 5:30, there's a 90-minute window there. So what I hope that I see several DOTs, several cities across the country on the webinar, I would say if you look at that, a corridor, an 8 intersection corridor, and we've done several of these around the country, sometimes they've been 20 intersections, but to be able to, at a glance, look at the entire network of signal system over a 24-hour period and identify what intersection and what time of day, that's a powerful use of connected vehicle data, in my opinion. So kind of the compare and contrast, July 2019, you can look at two intersections, the one on the left, you see all that red, that's an intersection that has lots of split failures. This one on the right is one where we got nice progression through. I'm gonna just reiterate on Luke, when you kicked off this telecon, you said, what you kind of asked that question, what can we get for feedback? And I hope these graphics, Luke, I've teed up, and if you want to unmute and ask any questions, feel free to, otherwise I'll keep going. But what I've tried to do is show at a high level how we can look at the corridor in terms of arrivals on green and whether we have sufficient green time allocation. So I haven't heard any question from Luke, so I'll just move on.
I'm here, Darcy. I was just playing with the mute button. So there was one that came in early doors actually, and you've sort of spoken to this already, but I think it'd be nice as a sort of a 360 view. I think that's around deficiencies on the roadways. I think this has come from an agency. So you were talking about obviously on green and whatnot, but what can you know from sign condition, pavement marking issues, potholes, collisions, bad drivers? Is that stuff that you're seeing? Is that stuff which potentially Blair or Matt can speak to as well? But does that wrap up, I think, quite nicely, a lot of what you were saying? Yeah.
I think really good comment on that. We might defer the pavement condition one to Blair towards the end. I'm a huge believer in that, but in general, this I am focusing on our work is that time space trajectory of the vehicles driving through the corridor. What you're talking about is enhanced probe data that I think actually is very attractive and got some longer term applications, but maybe beyond what I have in the slide deck right here. And Wejo will put a link to a session where we're going to do a deeper dive into this. We have a paper in at TRB, so if anybody wants to look at that in January, they're welcome to. The last thing I just want to talk about is scalability, because I think many of the partner agencies on the phone are going to say, well, does this scale? And I just want to talk just a little bit about, just show you around the country. Wejo was kind enough to provide us access to some data in California, Connecticut, Georgia, Minnesota, North Carolina, Ohio, Pennsylvania, Texas, Utah, and Wisconsin. And it's just staggering that 1 hour of data, you got 23 million points coming in, or 26 million points coming in here in Indiana. And we store that out in the Google Cloud. It's very cost effective. We have done several selected corridors with our pool fund partners around the country. So I showed you an 8 intersection example here in Indiana, but we've done some larger ones. California, we did a 19 intersection corridor, just went over with them last week. College Station, we did 22 intersections. Ohio, we did 21. So this scales really, really well to those corridors. I know I've tried to kind of step up the pace so we make sure we got a chance for question. I think the key message I hope everybody takes away from this talk is that the connected vehicle hard braking events that I showed earlier, if we can in 1 month get indications of emerging safety problems, whether they be along a signalized corridor, or I talked about last month along an interstate, those are absolutely, to be able to shorten that time frame for decision making by traffic engineers is going to save lives. And Wejo, if you haven't already put those out there in the chat, you can put some of those animations and some of those links to papers to kind of give participants some further reading. The connected vehicle trajectories, they can tell us how well our traffic signals are synchronized. Everybody loves to drive down a corridor and get a continuous green as they move down through. And we can identify, I hope I've shown you on here, how we can use that connected vehicle data to identify locations and time of day to target improvements. Number 3, when we pull up to an intersection and we don't have sufficient green time, those are probably some of the most frustrating moments as a driver, when we sit through one or we sit through 2 or 3 cycles. Sometimes we call those cycle failures, and we don't get to move through. Those connected vehicle trajectories really can help us pinpoint where those time of day, what time of day and what location those problems help occur. And that helps agencies systematically identify at scale where to allocate resources. And I think the last point is, I hope the graphics that I've shown you as I've gone through this scale well. And I can't emphasize the importance as we get into this big data with billions of records, the importance of having graphics that not are just pretty, but have substance, so that we as decision makers can then make tactical improvements to our traffic signal. So last concluding comment, Blair, Luke, Matt, I opened up, our vehicles know more about our signal systems than we know. I believe this is an incredibly exciting frontier for us at the university. It's incredibly exciting for practicing traffic engineers. And Luke, your question is a little bit broader than this, but I think it's spot on. Our vehicles know more about our infrastructure than we do, and I think that was really your hard break, or your pavement quality thing. So with that, I think I've timed this, so we've got about 15 minutes left for questions. I know I went to a little bit of warp speed there to keep us on schedule, but I hope we can move into some interactive discussion, because to me, that's the best part about webinars. So Luke, over to you.
Yeah, thank you, Darcy. I've got a couple of questions for you, actually. I'm going to bring, obviously, Matt and Blair in a moment. The first one is a question from Prasad, actually, which was your definition of hard braking. I can see there's a piece there in the chat, but I don't know if you're able to give, are there standards in this definition? What are you using? How is that being templated across everything that you're doing?
So maybe I'll volley that to Matt, and I'll put the animation up there
Sure.
while Matt gives the answer on the numerical value for hard braking.
Absolutely, yeah. So the definition around either hard braking or rapid acceleration is either plus or minus 2.67 meters per second squared, to get that right. I would say in terms of the general kind of standard, we are generally seeing that as a typical industry standard across kind of OEMs. But I think what's key around that is, a big part of our business model is to actually employ a common data model, so that when we are applying that kind of definition of hard braking, we are talking about the same definition across multiple OEMs. So that's the kind of the threshold and definition that we employ.
And Luke, maybe just I'll add one comment. I think the key thing on what Matt just answered is that high degree of correlation on what they're using right now for hard braking, that they're standardizing across OEMs, is very highly correlated with what we're seeing on crash records. And this is 5 years of crashes along a signalized corridor. So if we can do that with 1 month of data to get emerging problems, that allows us to be much more responsive. I know I've hit that point multiple times, but this is something that is going to save lives, and it's going to save lives soon.
Thank you, Darcy, and thank you, Matt. This might be for both of you as well. It's a question from Adam Moser, you can see, which is, how do you compare this data with high-resolution detection data, and does this compete with high-resolution data for implementing traffic signal performance measures? Darcy, that was to you. Do you want to go first?
Sure. So thanks, Prasad. I am still a huge, as you know, we've worked in this space of high resolution traffic signal data for a decade. And we still need high resolution data for second by second tactical response, because not every vehicle will be a connected vehicle, but for us to be able to characterize the performance of an arterial or any system using those vehicles out there on the road, and not be dependent on have sensors installed in the pavement or the appropriate high resolution data logger in the cabinet, what that'll allow you to do is you're trying to maybe stage your investment of infrastructure upgrades, is to look at a couple hundred signals and say, okay, what are the 20 or 30 signals that I want to prioritize for making infrastructure investments? So I believe they're complementary, but I do believe that we can get a lot of the results that we used to only be able to get with high resolution data from detectors, that as the connected vehicle penetration improves, is going to start to replace that for performance measures. Over to you, Luke.
Thanks, Darcy. A question back actually to Matt. You spoke about hard braking. A question from Edward Mark. I think that's from New York DOT. Hello, Edward. And the question is, has Wejo hard braking data been correlated with road conditions, i.e. wet pavement, snow, ice, or rubber?
Yeah, it's a very good question, and it kind of probably leads on to, as you can imagine, we are continuously unlocking new sensors, new attributes within the vehicles, and most recently, actually, with our newly onboarded OEM, we have actually started to be able to correlate things like autonomous emergency braking or hard braking with external temperature. And in the main, you start to understand, even down to the point of understanding wiper interval or wiper status in conjunction with the external temperature. And we find there is a definite correlation. And actually, if you can start to overlay hard braking with, -5 outside, you then start to build up that understanding of what's the potential of a, high-speed fatality versus somebody just potentially, slamming the brakes on and skidding maybe 10 yards as opposed to 100 yards. So absolutely, it's an application that we are starting to learn more about as we start to leverage more and more sensors in the vehicles.
Thank you, Matt. And a question probably to the Wejo folk, but also Darcy, I'll invite your comment as well. It was a couple of points that came up around privacy. I think one was from Catherine Wild. Thank you, Catherine. And the other was from Blaine Leonard, which I believe is Utah DOT. And to Blaine's question is, if you have location accuracy within 3 meters and can trace a path of a vehicle beginning to end, how do I assure my citizens that I protect their privacy? If I know how fast they traveled and where they're parked, my citizens may think we will we'll issue them a speeding citation. So it's a question around how much can you know without invading that privacy conversation?
Sure.
Matt, over to you first.
Yeah, no problem. So yeah, absolutely. Privacy is paramount to everything that we do, and the Adept platform that we have is built with privacy by design. Now, the data itself at a high level is completely anonymized. It cannot be traced back to an individual, and we take that kind of any attempt to reverse engineer the data very, very seriously in any of our agreements that we put in place. Now, I suppose, as a UK company, we have to be GDPR compliant, but also when we start to look at, for example, CCPA, all of this is around location data is something we have to be very, very aware of. So at a very high level, the data is completely anonymized. It can't be traced back to an individual. I think we also have ways, for example, if it is the start and the end of a journey, for example, we have the ability to obfuscate, the start and the end of that journey just to alleviate any privacy concerns. And then I suppose the final point I would probably highlight on that is with our granular 3-second vehicle movement data, because of the fact that device ID recycles over time, you can't then build up a picture of that particular person. So we take, privacy very, very seriously, and we take a lot of steps to address that and make sure that there are no privacy concerns around the data.
Thank you, Matt. Darcy,
Luke,
I know you're coming from a research point slightly different. What are you seeing, and anything to add?
No, I think Blaine had a really good question on there, and I think I would dovetail on Matt's answer and maybe add one more layer on that. Is I think as we think about agencies procuring data, the view that I think is much more compelling is the view that I show up here on the screen, and as we use, as Matt talked about, we don't look at the whole trip journey from a signal system operation. Our interest is how does this overlay of vehicles traverse through an intersection. We don't care really what day and what exact time, exact second by second of the vehicle going through. The more that we can identify ways to not aggregate this data into meaningful performance measures that tell us about how our signal are operating and get back those composite views rather than actually bring data into agency servers that show trajectories. I think that's going to be the other part of this. So making sure that the provider has appropriate anonymized procedures, but probably more importantly, identify the critical performance measures we want to extract out, so we never even have to see data that could be potentially try to reverse engineered.
Got you. Thank you, Darcy. I think there's a comment come through privately from Ed Market, New York, on a project task for a pilot they're looking at, and that sort of teases up a question that came through earlier. And I can't remember who asked this, but thank you. It's, are connected vehicles driving through a test bed, or are they in open roads? I guess the answer is both, but could you share more on the sort of information you learned from each setting, from pilot to real test?
Yeah, so to probably clarify that point, all of the vehicles that we feed and that are in our DEP platform are real life privately owned vehicles. So none of these vehicles are kind of running around on a test bed to simulate anything. And I think that's what's so unique about this data set, is the fact that it represents that true commuter behavior. It really does. Darcy can testify, better than anybody, but we actually do see those peaks and troughs around commuter behavior at kind of 9 a.m., 5 p.m. So, all of the vehicles that we have are real life vehicles that are moving around, the roads.
Fantastic. And then we've got a few minutes left. So I want to sort of give a look to the future, Matt. Connected vehicles, what does the future look like? What are the big limits from a Wejo perspective? What are you seeing from OEMs, from DOTs, and what might a landscape look like 5-10 years from now?
Yeah, absolutely. So, we have a fairly robust roadmap laid out, and I think there is a mandate that as of 2030, 95% of vehicles have to be connected in some way, shape, or form. Now, connected vehicles have been around certainly in the US since I think 1996, but we are increasingly seeing connectivity becoming a lot more advanced. We start to look at things like edge processing within the vehicle itself. I think it's fair to say, our roadmap has, certainly by the end of next year, if I've got my numbers right, we are going to be probably up to around 6 live OEMs. I think what we are typically seeing in the market around kind of being able to use connected vehicle data to influence safety on the roads is that OEMs are becoming a lot more. The realization is dawned that actually this we stand for data for good. So the data itself can be used to influence these kind of traffic simulation models, around the harsh braking piece. So I think the limitations, probably our own internal capacity. It's a nice problem to have, I think, is where I'm kind of going with that, in terms of being able to actually leverage all of this data, and that roadmap will only grow in terms of sensor breadth, in terms of in terms of actually being able to leverage things like autonomous braking. I've touched on a couple of them around wipers. That roadmap will only grow and grow as we start to use grow the use cases out.
Thank you, Matt. And Darcy, to you, you're sort of looking into the future for us, and also from a Purdue point of view, are you seeing this research rolling across more states? Is it going broader than this? And what's the plan there?
So I guess I'd answer a short game and a long game. The short game is, I believe that like in the next year, the consulting community is going to take a sharp pivot away from doing manual counts at traffic signals to assess performance and start purchasing this data, because there's no way you can get the statistical penetration by doing one count for 8 or 10 hours and run into a model that you can get with connected data. I think that's going to be the near term. Longer term, this enhanced data that Matt talks about, I'm incredibly eager. Winter operations in the snow belt in the United States, when the anti-lock brakes, traction control, when those events kick off on the car, that's very powerful information for us to identify where are bridges having slick spots. So I'm incredibly excited about the opportunity of these new anonymized data sets coming off so that we can do a better job operating our infrastructure, safer, better, faster, cheaper.
And then I guess my last question to each of you is, as we move this dial forward, if I was to present to you the likes of Wejo, who are doing some really, really intelligent things in collecting and using that connected data, your OEMs, and then your DOTs, who do you think are maybe the most important out of those three moving this forward? Who has the most to do?
I think in terms of their component parts, I don't think one can succeed without the other one. For us, we say this all the time in terms of we see spikes in the data, we see abnormal behaviors at certain points of the day. What we don't have is that context that the likes of Darcy and the Purdue team have. We don't have the context around what is typically being seen by a lot of the DOTs on the road. So I think it's fair to say one cannot exist without the other one in terms of their component parts. And Darcy's highlighted a very, very key word for us there around partnerships, and we do absolutely want to form partnerships.
Yeah, so hopefully I wasn't distracting there, Matt. But I think it's the key. I think agencies have built roads. The automotive folks have built cars. That's worked well for 50 years. But we now need to start integrating. There's several people on the call. I mean, Blaine chimed in. Blaine in Utah has been a huge thought leader in getting some of those partnerships going between DOTs and the automotive industry. We just got to keep stepping on the gas and find those new partnership opportunities.
Fantastic. Well, look, Darcy, Matt, I'm going to stop us there. We've reached the hour. We've had a really good, loads of questions coming through. Now, folks listening, this webinar has been recorded. It will be shared with you this week. Just allow us to centralize it and put it onto our website. We'll send it to you then. We've also got all the questions collated during this. And if Darcy, Matt, Blair, I know Gijo's been showing some pieces as well, reach out to us all. We can share our information. We'll be saying, or come to me directly and I'll connect with the relevant folk. This is a conversation that is only picking up speed. So please don't be shy, and we're happy to answer any questions moving forward. So it's a big thank you from me, a big thank you to Blair, to Matt, and to Darcy. It's been a really, really good hour, and I think we covered a lot of ground. So thank you to the panel.
Pleasure.
Cheers, folks. I'll let you say your goodbyes now, and we'll see you on the recording. Cheers.
Thanks all. Stay safe, and many thanks for the time.
Thank you.
Big thank you.
Cheers, folks. Bye-bye.